In this video, we're going to learn about electron affinity. Electron affinity is the energy change associated with the addition of an electron to a neutral atom in its gaseous state. So basically, the more negative a value you have, the more energetically favorable it is for an electron to be added to an atom. And this has a general trend that you can observe is that it increases as you go up and to the right. But there are several exceptions to this trend, and then we're going to go over those in this video. As we know, nonmetals like to gain electrons, and this shows that. You can see in general it increases and becomes more negative as you head up towards fluorine. Now, three exceptions I'm going to go over. One, if you have in the second group, the alkaline earth metals, you can see that the first two values kind of deviate from that trend. You have greater than zero values, which means it's not going to happen. The reason for that is because if we go back to drawing Aufbau diagrams for atoms and showing their electron configuration, this ranks the orbitals in order of increasing potential energy. Anytime you have to, if you're increasing the potential energy of a system, that requires an input of energy. So going from a configuration of an alkaline earth metal, where you end in S2, the next electron is going to have to go into a p subshell, which is higher in potential energy. So it requires an input of energy. If you think back to Bohr's model, kind of like that, where it requires an input in energy to get to that higher potential energy state. Therefore, it's not energetically favorable. Additionally, you see that nitrogen has a value of greater than zero. So the reason for that is that nitrogen has one electron in each of those 2p orbitals. And in order to add an extra electron, what's going to happen is you go from having a nice, stable, balanced p subshell with minimal repulsion because each electron has its own orbital. Now you're going to go from that to having a paired electron. And when you have two electrons in the same orbital, yes, they're spinning in opposite directions to minimize that repulsion, but there still is an added repulsion by them both being right next to each other. So adding an electron there requires an input of energy because it has a higher potential energy due to the added repulsion. Now, the other thing you might notice is like, okay, well, nitrogen's greater than zero, but the other elements in that group, not so much. This is a result of the fact that nitrogen and second period elements in general, the only shielding they have is from that first energy level, which is super tiny. It doesn't have as much of an impact. So electrons in the same shell, because they're much closer to each other, have a greater influence on each other. When you get to larger atoms with this great amount of shielding, and then electrons in the same shell are so far apart, there's less of an influence that they have on each other. And then the third exception we're going to go over is with the noble gases. You can see that they're all greater than zero, and that's because any noble gas has a complete S&P subshell, a complete valence shell. If you're going to add another electron to a noble gas without the addition of a proton, which would change the element, and that's not what we're talking about, you're going to have to put it in a new energy level, which requires a dramatic input of energy in order to raise an electron to that point. So those are the general exceptions for the electron affinity trend, but recognize that the more negative the value, the more likely an atom is to gain electrons.